instruments. I'm working as a freelancer and doing firmware and occasionally hardware for this. And this is a workshop that I gave in Austria in 2018 with a few updates. It's actually pretty long, and it took a full day back then. And I'll share my screen right now. So we'll go step by step, and we'll end when the time ends, and then resume during the next session. Occasionally, I inserted blank slides, like in my presentation, and if the time runs out, then we end at the next blank slide. Right, so the structure of the workshop, you should be able to see my screen at this point. It is like this. Start with the very basics of somebody who maybe never tried machine learning or anything else, but does have some basic programming knowledge. I'll introduce a node-based scientific workflow, which is basically MATLAB in Python, which is called Jupyter Lab. And then I'll explain a few intuitive things about neural networks, and then progressively the data structures required for it, and then progressively we'll get to actually doing this in Python. So this is just an overview. You don't have to read all of these points on the screen right now. I'll return to this slide again at a slightly later time. Also, I think that maybe after every slide, I would pause slightly, and if you have any questions, I think we could clarify it immediately rather than having to wait until a certain break, because I think it will make sense if there is any feedback or any questions, then that we handle it as soon as it gets there. Right. I just want to make sure that you are seeing this screen.
It's fine. We can see it.
Yes.
Yeah, it's all right. So then we proceed to the next slide. So the rationale of this workshop is that I don't know if anybody tried, but most online courses that you get about this, they basically tell you the structure of the entire thing. They tell you about what layers exist. They give you a fair bit of maths, and like imagine you went somewhere to buy a car, and like you have a very let's say advanced salesman, and he could explain everything to you regarding every part of that car, except there's just one thing. Like they explain the principles of the car engine that is in front of you, but they don't teach you how to drive it. So you know everything about its internal structure, you don't know what to do with it. And that is how most online courses are. There are also many things that demonstrate machine learning with some standard sets like digit recognition or image recognition and stuff like this, and many of those tasks they're already solved, and there are lots of papers about them. And it's like if you want to do something new, or if you want to improve upon those things, it's very difficult to compete with large corporations that have infinite computing resources, and also that can hire 50 people to just keep looking into this problem. So unless you actually can think in machine learning and what could be done with it, then just by saying, or maybe I should apply machine learning with blockchain, perhaps integrating some multimedia into it, then so that wouldn't go anywhere. And I'm trying to address this in this workshop to try to give some intuitive understanding and allow people to think in terms of what machine learning can actually do. So what is machine learning? Well, neural networks, they're basically function approximators that you have a specific thing and you have a specific input, and you train it to recognize that this input should produce this output, and then the network spits something out. neural networks are comparatively poor at solving precise tasks. So if you have some equations or anything that you could solve with precise algorithms, I would recommend against using machine learning, because it's not going to be exact. And so machine learning, like people, is very sensitive to data representation. That means, for example, depending on how you present the data to a neural network, it will look at it in a different way. So, when you want to exaggerate something and make it present some statistical figure in the best light to a person, the same rules apply to neural networks. If you present some data which is very flattering in some aspect, then the neural network would actually interpret it in the way you present it. And if you have a linear scale where there should be a logarithmic scale, then you won't get far with it. Neural networks, they do require large data sets. This has been changed slightly. Like recently, there were some new algorithms that could derive things from relatively small data sets. But if we need a neural network to solve some task, like, for example, with HR hiring, or with labeling data, trying to detect some business strategies, or predicting a market, we should be talking about hundreds of thousands of examples that this network should be trained with. So if we just have some data collected by people, and there are just 100 examples, then probably neural networks won't be working with it, unless it's a very specific case where this is possible. And for any serious machine learning, a person should have at least a graphic card, a powerful graphic card from Nvidia. And if it scales up, then there should be several computers, or possibly something running in the cloud. However, with certain tasks, it's still possible to do it at home. And if you have a gaming machine, then lots of things actually are possible, like deepfakes and everything else that would work with, well, let's say, a relatively modest gaming computer that would already work with it. So what makes neural networks cool? What makes them something like that is worth our attention? So first of all, that neural networks can solve tasks that are not precisely specified. Like, we know, okay, we have this input, this output, but we don't really know all the details why. So we don't have the answer why. There's a certain correlation between inputs and outputs, and neural networks, they're able to find some patterns in the data. Sometimes we are not even aware of those patterns or the nature of those patterns. And neural networks can also solve fuzzy tasks that until now required human attention, such as speech recognition, something recognizing written numbers, or facial recognition, something that you can't simply measure width, height, and then get some result out of it. You don't even know what to look at, and neural networks are pretty good at it, especially recently. Limitations are that neural networks cannot solve impossible tasks. If you feed noise data, if you try to predict something that basically does not have a rule, there's a story about superstitious pigeons. A B.F. Skinner was training pigeons in the 1950s and was releasing food at random intervals. And pigeons, they naturally assumed, like animals, they thought that there's a certain thing that they should be doing in order to receive food. And with every new release, the behavior of those pigeons, it was becoming progressively more idiosyncratic, and they were dancing, they were doing all sorts of strange movements, and the truth was that there was simply no pattern. And the same happens to neural networks. You'll get very strange predictions. You'll get some data that makes no sense if you feed random data that actually doesn't have anything behind, or where the entire rule of deriving it is so complex that a neural network simply cannot wrap it around itself. More than trivial models, especially those that work with sound, images, and stuff like that, they do require graphic cards, and AMD graphic cards are not going to work. You'll need to have an Nvidia card at this point, because somehow the whole deep learning market wrapped itself around one company that produces those cards, and that's it. And neural networks also require data preprocessing. So if you have data sometimes in natural units, as in letters or images, or maybe some categories or numbers that are not scaled in a specific way, you'll need to somehow bring them to some coherent format, which quite often is the same thing as presenting it to a person for visual understanding. So you'll have to scale it somehow as if you were drawing it for a person to look at, well, in a numerical way. To work with neural networks and machine learning, to be able to do this at the engineering level, a person should have clear and precise thinking, because it's very unforgiving. It's still science. It's despite all the fuzzy nature of neural networks, it's precise science that requires knowing of how to build a specific model layer by layer, understanding what those layers do, understanding how data transforms from one position to, like, from one layer to another layer, and what happens there. Really rudimentary maths, unlike many people say that you really have to understand all the strange formulas to be able to implement it from scratch. This is not true. Just some basic maths knowledge, which with arithmetics, maybe a little bit of trigonometry, is sufficient. You don't really need to go deep. And intermediate programming knowledge that is required at this point. Still, there are some visual tools for making neural networks, but they're not advanced and you won't go far with it. So here we are again at the first slide, the structure of this workshop. First, I'll show this Jupyter lab, which is like MATLAB and Python. Then I'll go to a Google website, which is called Tensor Playground, and it implements a simple network that classifies dots like according to their position onto two areas, into two categories. Then after that, I'll describe the required data structures that you'll have to understand in order to do anything with neural networks in Python. Then there'll be some intuitive insight about how one could look at neural networks in order to have some intuitive thinking and have some implicit set of metaphors that could allow to jump like between ideas and manipulate with this like in your thinking, rather than having to deal with formulas and doing it like approaching it with a fork and knife, but just getting your hands directly into it. Then I'll explain fully connected networks, the difference between classification and regression, then how to train networks, convolutional networks a little bit, like I won't go into details, and some tasks and examples. I will not go into recurrent networks and overly complex networks in this workshop. And today, probably we might cover the first 3 or 4 items if we're lucky. So yeah, and there's another thing to consider, like there's a marked difference between computer scientists and computer engineers, and especially when reading something about neural networks or things we have to know about which source it's coming from, because my approach is engineering. Like, you actually want to make some things running. You don't want to philosophize and go into deep speculation about things, and especially one thing that I find like which would be outside of the scope of this workshop is artificial intelligence safety, because well, it's like pure philosophy and stuff like that, and quite often we get to the point like what a computer scientist says: this alien computer has an architecture entirely foreign to ours. We have much to learn from it, and we may have much to fear. And if you read articles or something that wrote by those people, they usually sound very nice, but they have nearly zero information about what you can do with it. And a computer engineer is like, bam, I got Doom to run on this thing. So you just, get things done. Right, so that's the last bit that the whole thing will end with. This is the last example. I'm just giving a small preview. I created my own data set by just producing vowels into a microphone in a very strange voice, like oh, ah. And I created a training set. There's some Python code that splits it into chunks and classifies all different types of phonetic letters like R or U, and then tries to match it in a recording, in a fresh recording that it hasn't trained on. And it works surprisingly well with very little code. So that's like where we end with at the end of this workshop. So this is a blank slide, and if you have any questions about what I was just talking about, that's the time to ask them.
Very good. Seems clear.
We keep going.
Yeah.
Right. So I created several ways of accessing this for the participants of this workshop. So these are basically the technologies that you'll have to have in order to access this. Like if you want to use it on your computer, then you'll have to install VirtualBox, and I have a virtual machine, an image that you can download with everything pre-configured there. So you just open it, and everything that this workshop is about, it's going to be inside. Editing and everything development is web-based, so you're doing everything within your web browser. So you'll need to have Python, numpy, scipy, Tensorflow, then Jupyter Lab is the actual environment. Matplotlib is the library which helps to draw graphs and everything else. And there are some examples and sample data that I provide. This whole thing is available for immediate use from the cloud, and it's going to remain accessible within a few days, maybe 3 days. If you go to this link, it'll allow you to enter your email address, and it'll get you to a separate instance of a virtual machine. I have about 30 of them right now instantiated, so it'll serve up to 30 people at this point if they register.
And we are 18 here, so I think all of them.
Yes. So
exactly. So we should all be able to use one.
Yeah. So this is available for immediate use. It's pre-configured. All the examples are there, and it'll stay there for like 3 days from tomorrow on, because it's very expensive to run it for longer than that. So I'll
okay, so
days,
if you want to follow along the workshop, you can do so. Just go to that link, register with your email, and you will be assigned a virtual machine with a Jupyter notebook that you can run along with the instructions that George is going to give you. All right?
So after you enter,
that's right.
After you enter your address, you will find the IP address of the machine you're assigned to.
It's you get the immediate address to click where you could go, and the password is machine learning workshop, all lowercase, with 2 spaces in between, 3 words. It's, yeah, if like for some reason that if for some reason that doesn't work, there's also Google Colab. It's also going to work. It's a little bit slower than the other one, but it still will function. And also a virtual machine image for VirtualBox is available also at the Google Colab link. It's a Google Drive shared folder, and there's a Linux virtual machine there that will work with VirtualBox if you install it on your computer. Then,
yeah, is everybody set up with the Jupyter Notebook?
yeah, the password is Machine Learning Workshop. If you go there, and you could create, like you'll see a part of the screen is going to be like this. So you'll have a Python 3. Well, you can you'll see a launcher with Python 3 in it, and you can just click, and then you'll get a new notebook that you can rename to My Test Notebook or something like that.
Has everybody been able to do this?
Yeah, Kurt, Aviona, maybe Chris.
Yeah, I'm following along. Yeah.
Yeah.
All right. I see some
yeah, me
thumbs
too.
up.
Me too.
All right. So if you have trouble with it, just let us know.
The password is written by Michael in the chat.
So this is an interactive Python environment where you could type things and get them executed immediately. In this case, I created a file called imports.py, which contains lots of default functionality that initializes TensorFlow and also puts lots of common utility functions and mathematical functions at the top level, so that you don't have to import or configure anything. It'll be available instantly. So if you type run imports and press Shift Enter is to execute a cell. So if you get to this, if you press Shift Enter, if you move to the same cell again and you press Shift Enter again, obviously it doesn't make sense to run imports again, but if you have some other piece of code and you like to change something and run it again in the same cell, then you can return to that cell and press Shift Enter again, and it will update. So that's just for whoever wants to read Python. That's what you have inside imports.py. There isn't much, just mostly there's imports you have and some utility functions. So that's not quite as essential. So the environment will accept any Python code. So if you do any Python other than what is pre-programmed in this workshop, you could basically execute virtually any Python. Any functions are at the top level, and this I already explained. There are functions like print and plot to display results. So, for example, you could test the environment with just doing this. If you type something like this and press Shift Enter, so it's going to look like this in your Jupyter Lab. There's going to be a cell over this, and you press Shift Enter, you're going to get a sine wave displayed immediately. So this code here, it just generates a sine wave for x. So it takes this construct creates an array of sine for x lying within range between 0 and 10 pi, creating 1000 points in between, inclusive including the beginning and the end. So the virtual machines that I prepared, they are not super fast, but they're good enough for training. If you're in Windows, then you might, like if you want to have a working environment with within your operating system running, then you might want to install Conda, which is a Python distribution specifically aimed at machine learning, and it has many packages inside. If you have a gaming graphic card from Nvidia, in that case, you can install GPU support, and everything is going to be running a little bit faster. And for certain models, it's going to be like 30 times, 40 times, 100 times faster. These are the keywords that you might Google in order to get any documentation or more details about it. And by the way, this presentation is also on Google Drive. There was a link to Google Colab before that. I wonder, Michael, Daniel, if do we have that link somewhere? Maybe we can paste it in chat again if it wasn't there before.
For the Colab?
Yeah, for the Colab, because this is also where you can get all info, things separately for this workshop, such as
yeah. Let me fetch it again.
I'll post also this PowerPoint presentation is also downloadable from there. It's a tiny bit different. I fixed a few typos, but it's pretty much the same. So I'll get to my Jupyter. So I hope that you can see it, and I can create a new notebook here. Oops. And I can, for example, say, all right, the x coordinates are going to be a linear space between -5 and +5 with 1,000 points in between. And then y coordinates are going to be, let's say, well, x square. But that's in Python means the power function to the power of 2. And then I can plot, and I can see a nice parable. Also, the things like anything at all, like we can leave this cell. Actually, let me put it back. I can change something here, so I can make it to the power 3, and I press Shift Enter, and it instantly updates. And you can also have several graphs, like you can have graph 1, and then you can have graph 2. And they overlap, and you can compare them. So in this case, it will make sense to make it between -1 and 1. So everything is interactive, and that's the way of working with these notebooks. So back to the presentation. The next thing is Tensor Playground. So either you could go directly to the link, like Google Tensor Playground, or you can click on the first example, and the link is over here. So it's basically a dummy notebook with just one link that gets you to this page. It's well, basically it's a neural network, a very simple neural network playground by Google, which allows you to experiment and understand a little better how these things work. So the screen is split into several sections, and There are training controls that control the rate of training and different parameters, activation, functions, regularizations, types of neural network classification, regression. This I'll go through it one by one when I change to this. So this is the control section, which specifies like a global, you can say, hyperparameters for this network. So it's this section over here. Then we have data, which represents the data set, and there are altogether four data sets here for classification. And this toy box basically works with classifying dots into two classes, blue and orange, and you could specify different data and see how what challenges a neural network of a specific type would have with this data. Then these are the actual layers that that you can pre-program and see how the whole network is doing. And this is the output, which shows the original points, and after the training is started, you'll see like there are kind of very faint looking right now orange and blue areas. They'll become very prominent, and eventually you'll see that it tries to split the space around those dots in order to classify those things. At the left side here, you could also see that there is like you could control the extent of the data. That 50-50 means that you generate a certain number of points and you split them 50-50. 50 are used for training only, and then 50 are used for validation. Those points that were never used for training before, and we check whether the network actually figured out the law behind it, and whether the new points are properly classified into those two classes. And here, presently is just a straight line, but it'll show two loss functions. Loss function is an error which the network produces between expected and a real prediction that it makes and the expectation that we expect it to produce. So right now, I'm going to my web browser. So that's the link to this web page. I'm going to send this link to the common chat. There we are. So just starting it with the default parameters, I can just click play and it starts training, and you can see the error goes down, and finally it figures out, okay, this is my blue area and this is my orange area. We can make this network simpler, so just leave 2 neurons over here, and then we see it struggles a little bit more. It doesn't have enough capacity to represent this shape. If we, like right now, we're using tan-h function, which is a smooth function. It's an activation function that crunches the data internally in a smooth way. It's not important to understand right now how it works, but the effect of it is that the boundaries of the network's prediction are smooth, and it creates kind of nice round shapes. If I switch it to ReLU, which is a much more efficient function in terms of computation, it will generate straight lines, and it will define the same data, and you can see that the solution space that this network found for this data contains straight lines. Now, there are some parameters like learning rate. What a neural network actually does, it has a few coefficients there, and it tries to gradually, step by step, change those coefficients in a way where it makes the output error, the prediction of a neural network, more precise towards what we expect it to achieve. So, and also for every data set, like for example, this data set, here I can show that I can even add more layers. This is a very tough data set for a neural network to recognize because it does not have data in a comfortable representation. Like if we look at this, what we basically give to the inputs, it's a horizontal coordinate and a vertical coordinate at every dot. And that makes it very tough for this neural network to converge on recognizing this space, and it just doesn't matter. I can, like if I add a few more layers, maybe a few more neurons, it's going to be much slower. But you can see it really struggles with it. You can see it really tries to wrap around this data, but it really struggles to do it. Like it found a hole between those two dots, and it thinks, okay, maybe I can sneak through and somehow make it kind of fit almost. However, if we change the input data and we say, okay, I want to have also the square of the input coordinate fed into this network. So it's as simple as just taking x, like coordinates x and y, those basically they're called x1 and x2. But if we also feed squares into this network, then yeah, we have to wait a little bit because it's, maybe I can reduce the number of neurons to make it run a little faster. You can see that squares themselves, they facilitate round shapes, and they kind of, so right now, this network already thinks about this data in a different way. Instead of seeing straight lines and edges, it's looking at squares, and not squares, but circles. It's looking at circles, which is facilitated by providing it with the input data squared. We can do this again with the smooth function, but it's still not very successful at replicating this thing. What we can do, we can pass also a factor of like a product of both coordinates and see if this will help. So sometimes it might take forever. Sometimes it takes really no time at all. It's mostly trial and error, and the general rule is if you see data like this, then you could think, so what kind of function represents this data better? Like how can I make this neural network understand this better? Like in which format shall I pass? You can see that it almost kind of, now it almost works. Like it still struggles, but you can see already you got the inner spiral. So this looks like something like this could be represented with sines and cosines, because it looks like something radial is going on, and this is what we get for the last data points. And I might switch off some of those bits. Maybe I'll just get those two also in, and let's have a look. And then yeah, I think really takes a while because I have a very slow computer that is made slower every year by Apple. Let's see if it works real like this.
We know something about that too.
Yeah. Used to fly back in 2016, but right now it's very slow. And let me just try to cheat a little bit. Let's see if this will work. I'll just take some layers out and you can see that right now it's kind of getting there, but still there's lots of stuff going on. In this case, we don't use any regularization, which means we're just saying that there is no penalty. You can look for the solution everywhere you want. And you can see it gets there, like already, it's building this blue line. This data representation apparently is a little better for the network than just sending it linear things. I'll try to switch off my camera for a moment because I think it takes some of my processor time, and let's see if that helps. There we are. I think it went a little faster. So you can see that there's blue areas here above. They're already kind of classified as blue, so we can consider it as a success because it mostly it's getting there. So if I introduce more layers, then eventually it'll get around this data. But what I can also do to help it is introducing regularization, which means that individual coefficients for every layer should not exceed a certain value. And if they do, then the network is penalized for doing that. And I can say, okay, please regularize it like this. And this actually makes it look for simpler solutions. So if before that it was exploring very complex solutions, right now it's trying to find simpler shapes that would represent this data. And you can see it can already perfectly fit the internal part of the spiral of this. So, and you can see it's, well, not really, but it's slowly getting there. Yeah, here it gets another shape. So this is what neural network training looks on the inside like. So if you take something and you start looking at it, it has lots of strange shapes that it tries to fit to the data set that is being fed into it. So you can see it's, yeah, a lot more successful right now. And I can tell you I tried this before, but I right now won't be demonstrating it because it'll take a bit longer to train. If you add a few more layers, it eventually succeeds at matching this whole thing. So what we just saw, maybe I'll try it. Let's see. Let's increase regularization to this, and maybe add another layer. All right, let's see if it works right now. So in this case, we are passing a coordinate of a dot, and we are telling which color it is for training, and then we are passing a whole bunch of similar dots, but not exactly the same, and telling and asking this network to classify whether it's orange or blue. And in this case, it tries to classify the entire space based on the training data. Yeah, I'd say that's good enough. Like you can see there's a hole here between, and it cheats by drawing through it. So obviously, like if you have some data with holes, some data which doesn't really represent whatever process you are trying to predict, it's best not to have holes, because this neural network is like a very volatile liquid that is going to seep through every hole available and cheat in every way possible. So you have to regenerated data a little bit to close those holes. And now this neural network is given this instruction that it should somehow separate those two shapes. Yeah. Those two losses that we see here, there's basically two graphs. They look very chaotic, but that's what they look like. And one of them represents the training accuracy. Another one is representing validation accuracy. The difference is that how well it can represent the training data versus how well it can represent the data that it hasn't seen before. So enough of this. I'll just go to the next slide and we'll discuss it. So first of all, neural networks, they require this function that I was showing above, whether it's a ReLU or tanh. It's a nonlinearity. That means that if you have a number, it kind of, the function has to curl at some level. It couldn't be just a straight line. Or internal transformations, like between layers, if that thing doesn't happen, then neural network is not going to be of much help. And two most commonly used activation functions are ReLU and tanh. You can have a look at this, like if you enter any of this inside Jupyter, so you'll see what those functions look like. So in this case, it'll look like this. ReLU function is a different kind of, it's a name for basically a maximum of a value that is specified and zero. So you can see here, it crops everything that is below 0, and it is just a straight line in the positive thing. And tanh is a function that slowly curves towards 1. So you can see that it starts as a straight line, but it never allows the value that it's passed it to exceed 1 at the positive end and -1 at the negative end. So it contains any value that's being passed into it between those values, between those two numbers. ReLU, as I already mentioned, it's defined this way. And the solution area shape, like what your neural network will give you as a solution, will depend on the function you use. If you use tanh, which has no corners, it's very smooth, it'll give you something that looks smooth. And if you use ReLU as a function, then it'll give you something that has edges. Activation functions can be thought of as Lego bricks, like in Minecraft, you make everything from cubes, so it looks or square, kind of at that level. Of course, if you zoom out, it kind of looks still nice. And for that, for example, ReLU could be used for classification of sounds and images, and it doesn't matter that internally it has some straight lines defining those shapes that separate dogs from cats. It still kind of, if it has enough neurons, then it will be able to represent the space well enough. And activation functions can be thought of as plumbing joints of different shapes. So if you just have a straight pipe, you can't really, there is no point in plumbing. The whole thing should kind of go through several joints and curl around and go behind the walls and back and front and stuff like that. And this curvature, like in this case, it's just a metaphor, but let's say mathematical curvature that kind of redirects a function, redirects a value from a straight line. So somewhere else is what makes neural networks work. And this is something that happens between layers. You know, if it's a straight line, then it doesn't matter how many layers you have. All of them like individual pieces, they all combine into a straight line, which is essentially the same thing. But if you have many curved pieces, then you can pretty much represent any shape. And that's what machine learning requires, some form of nonlinearity that could represent complex shapes of solutions. Softmax activation function is something, a third type, I would say, a very common type that is only used on the last layer of a classification network, and that converts your intermediate data from a complex neural network into a list of probabilities where you need to classify if something is a cat or a dog or a house. You use softmax at the last layer and it gives you a probability distribution. So that's the end of this section for now, and I think we're at 8 o'clock. I think there was a break schedule somewhere.
Yes.
I think we should.
Yes, we can have a 5-minute, 10-minute break. Which we can bring here later on. What I wanted to say is that unfortunately I couldn't find a link to the Google Drive. So please, George, if you could share that again. I know it was somewhere in the slides, but the copy of the slides that I have is a bit old, I think.
Yes, I think so. There it is at the bottom of this.
There it is, okay.
Like I have it a little bigger.
There you go, yeah. So I'm just copying it in the chat.
I have an extra W.
What?
I have an extra W there. I sent it to you by mistake.
I'm gonna send the correct one. Here we go. That's the one. So here, when I go here, there's something about the bookmark. Is it working for you?
No,
or maybe the link.
It's going to the front page. Let me try typing it.
Yeah. So maybe I remember we created this a couple of days ago, but maybe it expired in the meantime.
Did it expire? Yeah. Okay.
Maybe. Yeah. Maybe.
I'll give the full link right now to the chat.
Yeah. There you go.
Let's delete the message maker so not to confuse people.
Can I do that?
Yeah, it should be possible.
I don't know, at least.
I can copy it, but I cannot delete it.
No,
okay, let's just post the correct one.
How about just a moment? I think I might have made a typo in there. Would it work with MWM? It does. I think it's MWM, not N. So
maybe I did a typo then.
Yeah, you did.
No, I think I did. It's no, I know. Yes, indeed. It's fine on my slide. It's M. Yeah. Okay.
That one.
MWM.
Yes. Yeah. So good. My bad, folks.
No worries. Now it gets to the correct side.
Yeah, Jacobo confirmed. Thank you, Jacobo.
So, George, the regularization is to avoid overfitting, right?
A regularization is to avoid overfitting, and it basically imposes certain limits on the coefficients. Like it's like it makes it look for. Like imagine like if you're allowed to walk everywhere. In Malta, for example, you're allowed to walk everywhere, including on water and everything else and stuff like that. And this regularization is like tying some heavy metal weights to your feet so that it tires you down when you walk. So you instinctively are looking for kind of straighter paths and more optimized routes rather than going all over the place. You could understand it in this way. Regularization just takes the weights of it's going to be further in the presentation. It just takes the weights of the network, combines them in some way, either taking a power of 2 and then summing, or just summing the absolute value of them and adding it to the error. So
exactly, trying to keep the median or mean, I think, something like that.
Yeah, median it doesn't use, but mean basically, or just a sum, because when you're trying to minimize something, it really doesn't matter whether you divide it by the total number or if you just minimize it as is.
Mm-hmm.
Yeah, so yeah, in essence, it just penalizes the coefficients in a way that somehow works, but in theory it shouldn't work, but it does. So there are also other ways of doing it, like my favorite way of regularizing neural networks is introducing dropout layers, where you can just randomly drop 50% of all neurons. You have neurons, they're just half of them, and at every training stage, you just half of them ignore, and you just drop them and don't do anything with them. And
that's forces you to relearn stuff. That's why I think that one's good.
In this case, like if you introduce dropout layers, it kind of partitions network, and at every step, a different part of that network is being trained in a slightly different way. So you have some variety in the training that helps to avoid overfitting as well.
Are there any questions other people want to ask?
Everyone seems to be very quiet.
Everyone is so black boxing.
A little bit.
All right, so let's take a 5-minute break. We can be back here around 8:12. You can do 8:15 if you want.
No, I think 8:12 is fine.
Is that okay?
Yes.
Which time exactly?
8:12.
8:15, 8:12. Okay, fair enough. Fair enough. Okay.
8:12. Yes.
Okay. See you soon.
See you.
Okay.
Yeah.
Well done.
Oh.
That was so cool.
Let me get some light in the room.
Yeah, whenever you're ready. I think we're good, unless there are questions. Questions from the participants? Comments about the music? Really nice work, by the way.
Thank you.
No questions so far, so we can continue whenever you're ready.
Right, ready. So this section is about data structures in NumPy. Normally, this would require some trying things out, but I'll just go very quickly over this to the more interesting part. So in Python, you have lists, which are like arrays. They're called lists, and there are several versions of this data structure. Natively in Python, you can just open a square bracket, and then you can list numbers in this manner. Yeah, and then you have an array of numbers, and in this case, Python is rather tolerant towards the trailing comma. You can have it there, and especially working with large arrays or data sets, sometimes it's convenient to, when splicing them, to keep that comma over there. Then you can have nested lists, like two-dimensional arrays, where you could put arrays inside arrays, and then it kind of looks self-explanatory. And you have tuples, which are like lists, like arrays, but you can't change individual elements. It is stored like a single object, and if you want to change something, then you have to rebuild it. So that's a tuple, and reportedly they're more optimized under certain circumstances in Python, but essentially they are the same, like constant arrays. Now for tuples, this trailing comma might be important if you have just one element. For example, if you have just a tuple of one element, then you cannot just write it like, if you write 5, then it's just number 5. It's not a tuple, it's not a list, it's just a single number. And if you want explicitly to make a tuple out of it, then you have to write of a tuple of one element, and you have to write 5, comma, and then it's going to be a tuple. Then we can talk about shapes of these things. The shape is a representation, basically how many dimensions there are in a specific list. In this list here, you have 5 elements, and it's it's a list with 1 dimension, and and it has 5 elements inside. Therefore, the shape of it looks like just 5. If you have a list with 2 dimensions, then you can see that in 1 dimension you have 2 elements, and in another dimension you have 4 elements. Yeah. Then we have 4 on the outside and 2 on the inside, and the shape of this list looks like this. Then the shape of this one would be 6, the same way. NumPy is a library that allows working with those lists in an optimal way, while Python itself works with floating point numbers as in 64-bit, and also there are no built-in operations that process several items at once. With NumPy, you can have different data types. Machine learning mostly works with floating point numbers of 32-bit and sometimes 16-bit, but 16-bit support still today is a little patchy, so normally using 32-bit floating point numbers is good. And once you convert a list to a NumPy structure, which is very simple, like if you import NumPy as NP and you use this syntax, then it becomes a NumPy matrix or an array, what you think about it, that supports vector operations where you can combine sum, subtract, multiply, or do all sorts of things with those things with just a single operation without running any loops. You could transpose a matrix. A matrix is basically an array of 3 by 2. Well, in this case, yeah, 2 by 3, depending on how you look at it. So there's a transpose operation. There's a flatten operation that just expands it into one flat array. Yeah, you can slice, you can take, well, this is available also for regular Python, but we're talking about NumPy here. We can say, okay, I just want this middle part of it. So I'm specifying that I'm going to do it from the element number 0, 1, 2 to the element number 7. And the second bit in Python is exclusive in the sense that it does not actually include the index that you're specifying. And making a copy is like this, because everything in Python that is not a simple type is actually passed by reference. Means if you are doing b equals a, and you then change b, then you're actually changing a as well, because it still points to the same, essentially the same data, only it has a different label like a and b, but it points to the same data. If you want to make an independent copy, you have to use this copy construct. Reshaping arrays, sometimes you just want to change the representation to have it flip the dimensions or altogether change how it works. This is very important sometimes for machine learning that requires a single input, but this single input should be buried throughout some dimensions at the end. So you can change. You can make from an array that has just one dimension, you can make 3 dimensions if the total number of elements matches. And while reshaping, again, so if you multiply all those values, they should, like in this case, it's going to be 4 by 2 by 1, it's going to be 8 elements altogether. This h, like for any reshaping of this array, h should remain the same. Like if you're trying to somehow put a different value here, like 5 or whatever else, it will not succeed if a only has 8 elements to start with. And reshaping itself does not really change the, like it doesn't really make another copy or anything else. A reshaped array is just a different representation of the same data that is already in memory. The operations with NumPy, you could use plus to combine 2 arrays. If they're of exactly the same size and shape, then it's very simple. You just add the 2 and you get the result. So this obviously is the same here, and you get the result. If one of them is shorter than the other and just has 1 dimension, then NumPy automatically replicates that dimension and assumes this is the first one, which is the same thing, and this one is being replicated downwards, and then those 2 are combined and they give the same result. Or if you have a vertical array would look like, I'll just write it here somewhere. So if you have like 1, 2, 3, and those are going to be many arrays with 1 element in them. So that's what a vertical array looks like. Yeah. So it still has one element per kind of row, but it's positioned vertically. And horizontal array, if you trying to add those two, then it will expand both to a rectangular size, and it will produce the same result as here. So there are links to both, there are links to the documentation for scipy and numpy libraries. Scipy is, you can think of it as an extension of numpy, which contains many more algorithms for numerical and symbolic mathematics. And before any data is fed into TensorFlow or machine learning, especially if it's if the amounts of data are moderate, then you can do processing using those two libraries, and many metaphors that those two libraries use in terms of representing data and stuff like that, they still hold true for TensorFlow and machine learning libraries. A neural network can be represented as a set of layers that where the data travels from one layer to another, and there's a training process that trains this network to match, to somehow construct the layers in between, like the adjust the weights for those layers in order to get a form of expected output which matches a certain predefined value. So we have input data, like we have our faces or whatever else, and have output expectation, which tells us whether it's, for example, male or female or something else, or speech recognition. So training data, in this case, we are talking about supervised learning, where we know our input data, we know our output data in advance. And we need to train our network to learn how to match the two, how to produce output from a given input. A layer of a neural network could be represented as a mixing bowl. And you put your data in there, then you start mixing it. Weights, in this case, represent how much of the individual ingredients from input data you're taking. So if, let's say, we have a cucumber, celery, and tomato coming here, or something else, just some pixels or numbers and stuff like that, weights, they represent how many, in what proportion and what quantities those actually arrive in the mixing bowl or blender or whatever else. Then we have an activation function, which basically crunches everything together and makes it go into a curved line. And then this whole thing has its own set of ingredients, because this, when you mix it, it's not uniform. In case of machine learning, you have several ingredients coming out, but different ingredients compared to those that came in. Then you do this again in the same way with weights, and then you do this again. And you get some form of prediction. And neural network just has some weights, and it says, okay, I think that this input actually gives this result. So, which probably is wrong, because all weights are initialized to be completely random in the beginning. So what we do, we compare it with what we want it to be, which is called ground truth, through a loss function. Loss function is basically a form of difference between the two, and there are several types of them, but the simplest one is just we take the two, we subtract them, and we square the result. And then if there are several of these parameters at the output, then we do this to every individual parameter, and then we sum them together, and there is a certain error, a certain number, which in the beginning is going to be significant. And then we look at it and check how shall we change those weights so that this number would be smaller in the next iteration. Obviously, we cannot do this in one step. We can only predict this a little bit, like into the future, and say, okay, if I have a very small increment, then to all of those weights in a certain direction, then this loss function is predicted to be smaller during the next step. Not necessarily, but the method of doing that is called backpropagation, and it uses gradients and derivatives, which is fundamentally not very important to understand unless you are delving into this thing. The important thing is that it kind of takes small steps in specific directions that it chooses internally for each of those weights in order to change them to make the prediction a little bit closer to the ground truth. Weights start in random, and if you think about some data, some internal model that represents your process, you can think that with these weights, they kind of wrap around this model. And in the tensor playground that we were looking at before, it's visible how it kind of wraps around the data, and it does this in many, many dimensions, and not necessarily in 2 or 3 dimensions. Like neural networks can have thousands, hundreds of thousands dimensions with millions of weights. This is a good way of looking at it. The training is gravity, and those weights are kind of dropped upon a specific model that we want to represent, and they wrap around. And sometimes, like if you think about this as a physical metaphor, not every shape could be wrapped around. There are shapes that you absolutely cannot get inside, like for example, a sphere, a hollow sphere, or something else. And it's very important to kind of look at this, first of all, perhaps from an intuitive point of view, and then perhaps visualizing data somehow, making sure that those weights can actually wrap the data. So this is what it looks like mathematically, the structure of a neural network. You have an input layer where you feed your input data that you want to derive something from. Then there are hidden layers, a number of hidden layers here that do some transformation which might not have any meaning for us as people and might not look particularly great or good. And if we start analyzing what weights we get, sometimes we get nice figures there that gives us some insight, and sometimes we just see it as garbage and it still works somehow. Then there's an output layer that combines the last layer into certain ways that it kind of produces outputs. So for example, for this neural network, we have this many inputs and it produces 4 outputs, which if it's a classification network, then it could classify something into 4 classes, like a dog, a cat, a house, and a car.
George, to stop you for a second.
Yeah.
Is there a way to realize if we need to add an extra layer, for example, or reduce an extra layer? How would you go about that?
I would say that you start with a certain predetermined number of layers, like 3 or 4, and you
which is a random.
You put as many neurons as your hardware can handle within a manageable time. Like if it's a depending on your model, you don't multiply too many layers. You just start with a few layers normally, 2 or 3, maybe 4. Pretty much for everything that could, like, unless you have a very specific idea how to build a network, just start with a few layers but many neurons.
Mm-hmm.
So each individual layer could be very deep. So each of those neurons, like it's not really represented on this picture. It does it does have, like for example, if we take this one here or this one, it has many inputs, and those inputs are combined, and there is this activation function there. So each of those neurons, it looks like this. So you have a number of inputs multiplied. So this is the weights, it's a multiplication, then summed together, and then passed through an activation function. Sometimes you would have a bias, which is a constant, like a constant plus C also goes in there. So a constant does not depend on any inputs. It could be just 1 or 0, or it could be 1, let's say, and then without creating a special case, we have another weight which automatically trains. Then we have this activation function, which is relu or tanh or something like this, and we're getting output. So back to the question, there's one thing that it's good practice to start with a model which is large enough to possibly fit your data, and so it'll probably overfit, and more about this later. Yeah, I'm just reading on the chat here.
Yeah, that's answer.
Yeah, we have a couple of questions. So the first one is, what is the best case that I can use neural network in?
How do you mean that? What
yeah, I don't understand the question either. Shady, can you elaborate your question a bit? And Paolo is asking for neurons and layers, the more the merrier, or too many could produce bad results?
Oh, yeah, that's a good question. There's a difference between at which point, because if we talk about the width of the individual layer, like if we talk about this vertical space, the more the merrier, I would say, if your hardware can still handle it. Like if it takes 1 second to train and then you expand this to several thousands and it still takes 1 second to train, then it's good enough. Like you don't have to reduce this number. Like optimization can come at the final stage, but in this direction, you can have as many as you want, and the more the better. In this direction, like the number of layers, this could confuse network and prevent it from training. So as a rule of thumb, normally start with, let's say, fewer layers. Because if you start with too many, you don't really know, it might take forever to train, and you're going to be getting bad results, and you won't be understanding why.
The feedback loop would be very long, I think.
Yeah, if you start like with 2 layers, for example, and you see it doesn't train well, you can add another layer, and you can see, okay, it improves. That's good enough. If you decrease, sometimes you decrease layers, and the generalization performance of a network improves. Okay, I have a clarification here. What is the machine learning problem that we can apply neural network to solve with accepted accuracy? Basically, classification problems, like if you have several cases of something like financial fraud, download ratio bots, for example, detecting real responses from fake responses. You could detect, there's a thing called sentiment analysis. You could use a neural network to detect whether your product review is positive or negative. Like from the text that is written there, you can figure out if it's a generally a positive review or a negative one without having an explicit score. Accepted accuracy in regression cases. What are we talking about? What kind of regression? Yeah, I'll just keep going here. So, right, so we start with a fewer layers, but lots of neurons, and we should basically fit, change it according to what's reasonable, because ultimately you want to be running this network again and again within a reasonable time, because if you have too many of those things, it will take a day to run, and then you won't have any feedback from what your network performs until the next day, and that really for any research that slows things down to the point where sometimes it's impossible to go forward. Especially in the beginning, you really want to know fast response, and that is what limits the size of the network. So representational capacity, basically how large the model is, how well the model can represent target data. And but it does not guarantee that the network actually can predict anything useful. What it does guarantee, well, it should guarantee that the network can, in theory, fit your data. And there's a thing called overfitting, when the network attaches itself too much to the input data, and it is still unable to generalize for unknown examples that it hasn't seen before, but at least it's able to detect those examples as it was training on. And if a network can overfit, that means that it is usually large enough to represent the data model. So in this case, starting with a network that overfits, that attaches to the data too much and has too many neurons, is a good thing. It's not a good thing as we go through, but without making sure that it can potentially overfit and that it has enough neurons to represent the data, we cannot take the next steps to optimize and tune it. Now there's a learning rate. There's a learning rate, which is one of the hyperparameters, like we do have this in our tensor playground. We can see this as learning rate. That is the size of the step that is being taken by a network in every iteration in changing its weights. And if it's too small, it will take also forever to train. And if it's too large, like we can see what happens. Like usually, as a rule of thumb, I start with something at 1000s or 100s, with like, regardless of what model you have, usually starting like around that value gives you a certain base point. Like obviously every network is different, and sometimes you're starting with one works, and sometimes you have to go to a much smaller value to make it work. So this is what learning looks like when this rate is too high. And it kind of, like in this case, it tries to find the bottom of this function, and it never manages because it kind of overshoots every time and then jumps and never actually goes in there. And if it's too small, then, well, good luck waiting for it. Also, sometimes having, like in this case, it might seem that having a smaller learning rate is better, and that eventually it would learn better. That is not necessarily the case. Sometimes you want it to jump a little wild, especially in the beginning, to kind of get an approximation of data, because if you have a very small learning rate, then you never get a chance for those weights to change enough to kind of maybe look for a different solution. Or like if you have a function that has several dips, like if it started looking at some local minimum, because the learning rate is so small, it might never get out and kind of find another one. Generally in machine learning, like if you use regularization and dropout layers and stuff, it's not really a problem, but still learning rate is what constrains the time it takes to train the network. Classification and regression, those are two different types of networks. So in classification, you are trying to predict whether your input belongs to a specific class. And regression means that you just have an input function and you're trying to predict the output value. For example, it might seem that for predicting cryptocurrency, let's say trading rate, you could use regression rather than classification, because you have a certain graph that represents the past value of that currency, and you need to predict the next value. It might seem that you would use regression because you need a continuous value, like a continuation of that graph, but that usually does not work very well, and you would still use classification even if you want to predict a single value. So this is a typical example of a textbook classification where you have, let's say, you classify as an image, and then you have a probability distribution at the output that tells you which class this image belongs to. But if you predict some, you know, if you do some market trend prediction, then you could look at it also as a classification problem in this way. So you have several classes, and you get a probability distribution for the trend going up by more than 1% or within 0.5% steady, or going below. And this would work better, and I tried, it does work better than just trying to predict the value directly. Moreover, this actually does give you a certain measure of confidence. Like if you see, you can think about it like we have, let's say, 5 classes. 1, 2, 3, 4, 5. And our network predicts that it's mostly likely class number 4, but also there's a certain probability here and here, and maybe a little bit here. And there is no, like, let's say this is very close to 0. We can see that this is a result that it has a certain measure of confidence, but then we could also look at it and the neural network could predict something that would look let's say those values are going to be much, much closer. And you can see that in this case, like in the top case, the network is fairly confident that it's number 4. In the bottom case, it's, you can't really tell. It most likely it's number 3 according to the prediction, but it could also be something else, and the network is less confident about that. So in this case, you have this, and also multimodal things where you could, where something could be equally a bird and a cat. You could have probability of something like this, and also thinks that it might be another one. So that also works very well with classification, something that you can't really do with regression unless you have several outputs, each of them being regression. But then this whole thing explodes like in complexity, even at the conceptual level. Softmax activation is something that you have to be using for classification, and it's the last activation function. If we looked at the neural network, then the very last activation after the last node is going to be softmax, and it generates probabilities from some random data, seemingly random data generated by a neural network. Before softmax, the data can look like this. Okay, we can see this kind of makes sense, but then there is this value, and they're not scaled. They are represented in some strange unit of measurement. After softmax, they look like this, and they all sum to 1. And they represent probabilities for those outputs, for those 5 outputs, 5 classes. So this is what softmax does. And you can see that it emphasizes this, like a 225, and this is just 1 and 217. You can see that they're all scaled, and they're a little bit more emphasized towards, you can clearly see that which one is bigger. Softmax is using exponent in its formula, and that's the definition, the mathematical definition for softmax. So you basically, for every output, you take the like e to the power of that output, and then you divide it by the sum of all of those powers for every output. You can see that we do have a power function here that it goes to an exponent. Yeah, the second bit here, I think I jump through. So this is how you represent it in Python. You never need to do this directly because there are functions that do it for you in TensorFlow. So moving on, can you explain softmax function? Yeah, Shady asked a question about explaining softmax in multi-classification. Softmax in what sense? Like, for example, if we have it, in order to get probabilities, the softmax function should be like put at the last layer after everything, like we have.
I think George, if you draw the softmax function, it would be understandable.
Yeah.
Now if you draw the what is it called?
Yeah, if we look at this network here, then we kind of implicitly assume that there is an activation going on before every neuron. So the activation function that will go before the last layer here or after, it depends on how you're looking at it. So basically the last activation function that you ever use in conjunction with a certain neuron is what softmax should be. So if you use something else like rel or tanh and it's a classification problem, the last one should have softmax. So softmax guarantees that all your outputs sum to 1, like a set of probabilities should be. Like you can't have probabilities sum to something other than 100% if you look at each and every case. So if something belongs to a certain class, then the sum across all classes should be 100% always. Linear networks are networks without activation layers. And this is something that is quite useless and it could be used for linear regression. It's basically like fitting a certain set of lines to produce a result. It's equivalent to single layer networks. Like if you don't use any activation functions, your network could be collapsed to just one single layer, and it's going to perform mathematically identical. There will be no difference, and there is no magic in these networks, and so you always need to have some form of activation function. Linear networks cannot be used for classification tasks because for classification, by definition, you need to have at least a softmax at the end. However, just for learning, you could use linear networks to demonstrate regression networks, because you can see, okay, this is my data and now it fits a straight line. So I could use regression, like I could use linear networks for this. And let's get to actually, let's get to the first example. I'm going to show how this works in practice, and actually I will use the linear network here. So this is the first example. Yeah, first I'm running imports. And this was just what I mentioned before. Also in Jupyter, like for example, if you're a student and you're preparing some documents, you could also have some annotation cells like this. This is basically a markdown language where you could just specify any data. And then when you press Shift Enter, it turns into a nicely formatted piece of text. So to plot something, you that's from the beginning of the workshop where I showed how you can plot things. This semicolon at the end I add to prevent some garbage in the output. Like if you have this, you have some additional rubbish, and to suppress it, you put a semicolon at the end. The scatter plot is just like you have x coordinates, y coordinates, and then it looks like this. Now, this is a TensorFlow Keras. Keras used to be a separate library, but now it's integrated, and it is the most popular TensorFlow API. That's how you create a network in TensorFlow, in this case, just sequential layers one by one. And I'm creating a dense layer, fully connected with the input shape, 4 inputs, 4 units in this layer, and then another layer of 4 neurons. I'm using I'm compiling this model, and I'm using an optimizer Adamax. This it's like there are several of those optimizers, like stochastic gradient descent. Then there are this adaptive nester of momentum and stuff like that. The thing is that the optimizer basically decides how to change your weights based on like how to change them for every step. And some of them do not just track the direction of motion, whether they're improving or not. They also track the velocity, like how far the change is happening, and they adjust it according to a whole bunch of parameters. It's not important because every couple of years they invent new optimizers, and some of them work better than the others. And there's a whole Adam series of optimizers that work pretty well, and Adamax. Adamax, I recommend it as the baseline optimizer. There are other types of Adam, but sometimes they explode and they produce numerically invalid results. And Infinity Adamax, it seems to be stable as it's constrained inside. But my favorite combination, actually, which didn't exist when I created this workshop initially, is using a look-ahead optimizer with, I think this would be a way of specifying it. So it kind of uses rectified Adam optimizer on the inside, and then it creates a specific look-ahead logic. And there are papers written about this. I won't be going into details, but that combination seems to, like in any practical results, I tend to more and more use this specific combination, and it does seem to work best. But for simple things that, let's say, give a fairly fast convergence rate and at the same time don't explode badly, Adamax seems to be one of those that behave more or less predictably. So this model summary prints what we have right now. We have dense layer for dense layer shape for this none here. Like if we use batch training, if we train several examples at the same time, then it would substitute this with the actual number of examples fed in one training step at the same time. This is the number of parameters that any given layer has. So 4 units, 4 inputs. That means 16 parameters, 4 by 4, plus an additional 4 parameters of bias, which is basically a constant shift, which is added like a constant added together to the inputs. And I'm using mean squared error, which basically takes the predicted inputs, takes the true predicted outputs, takes the true outputs, calculates the difference between the two, it takes to the power 2, and then sums them together. Yeah, the number of, like, it will be growing. If I keep running this network, it will keep creating new layers. That is of no consequence. Like if you really need names, you can specify them manually. This is our input data. In this case, we have 2 examples, like 1, 2, 3, 4, 7, 8, 9, 10, and we want this network to continue the sequence. So the output data, so this would match this, and this would match this. So we're just saying, okay, it's a linear network, it should be able to predict linear progressions. So now we call, like this is also no consequence, we could call this. And it starts doing something. There are a few extra bits because sometimes, especially for long training sessions, you do want to save your training status periodically and training state of the weights of the model. Because if something happens to the power or something just then you lose your training. You have to restart from the beginning. In this case, you can always recover it back from where it stopped and continue even if everything goes out. And basically, there is no specific meaning in this. It's like you could just copy and paste this and it will work. And that's another one which monitors the actual training loss for like if things are moving too slowly and doesn't do anything. It assumes that perhaps the model is being, well, the model is stuck within a specific place and it doesn't want to continue, maybe because it overshoots and it reduces the learning rate. So after, let's say, 100 epochs, it sees, okay, there is no change, I should reduce the learning rate by this factor. And that's also something that could be changed. An epoch means that the training went through the entire data set. Batch size means that we are training, in this case, both examples at the same time. So I'll show how this works. I have slides about this. So now we start this. Actually, I did train it already, so let me just restart it quickly. It does produce nice graphs, but only if you do it in the correct order. So I just chose this option, restart kernel and run all cells. So it goes cell by cell from the beginning. And now it will train this, and after this it will plot. So this is what we call a loss. I took a logarithm of this loss, and that's the error produced by this network within this training data. In this case, I don't have a special validation set which allows me to prove whether this network works at all or not. I'm just checking it on the training data on which it was training, and it's logarithmic. So actually, if you check what it really looks like, it actually looks like this. But taking a logarithm allows us to kind of look at it a little better. So network is trying to fit it, and then at some point, and it found it. So this rarely happens in real life, but in this case, it found a solution, and you can't get any better than this. And here we can predict. So if I tell, okay, this network, please predict 6, 7, 8, 9. What am I having? 10, 11, 12, 13, which is kind of okay. What about this? Just a different linear sequence. Well, not quite as precise. You can see, but let's say, what about 8, 9, 10, 11? Yeah, still works for this range. You can see, like if I'm going wildly out of range, then it would reduce in precision, but still within this range, it works okay. I think it would also go for 1, 3, 5, 7. Well, doesn't work so well when there's a space in between. Yeah. I have a few questions here. Like, does increasing number of epochs if it gives better accuracy, or if it will lead to overfitting? It depends. Like, if you depend on early stopping, if you want to stop before it starts overfitting, then if you have this model checkpoint and you monitor validation loss, which, well, in this case, we don't control for overfitting, but with validation loss we would, then it'll save it at the right point, and you can keep training it, and simply nothing will happen. But if it still didn't converge, then it will increase precision. This checkpoints will be created at the best values of training. So if you go past the best value, you can still kind of roll back and take the best one. So normally increasing, well, if you don't rely on early stopping and if you use other methods to prevent overfitting, then having more epochs generally is a better thing. But sometimes you can just see like the network is not training anymore, and this is where you can stop. So let's see. This is what I did within that thing. So there's a sequential type, means that it's a directional graph of just one layer connecting to another layer. There aren't some, strange branching nodes or simultaneous layers that do it, like twin layers or stuff like that. A very simple sequential network, and I'm specifying layer by layer. Then I'm compiling it. And for compilation, I have to specify an optimizer. Adamax is a good one, with the learning rate of 0.002 and squared error loss. And then when I'm typing model summary, I'll have all this printed, and it will show all layers and how many parameters it has. And it says it's a pretty good thing to have an overview of what model you're running. So this model that I just built does not have any activation layers. It just has 2 length layers. And basically it's going to be equivalent to a single layer. I actually, I haven't tested it, whether I will need to have more units, possibly not. So if I just kill this one and compile, and then train it again, then it probably will work as well. Yeah, it takes a while. Like in the second example, I have a nice, neat scroll progress bar. So yeah, this looks boring. Well, it's still good enough. And if I put here like 7, 8, 9, 10, it works. Yeah, so it's a linear one, doesn't have anything in between, and the data. So that's the list of inputs I had, and then I have a set of matching outputs which correspond to those inputs. So for example, this one will be matched with this one, and now this one will be matched with this one, and this one will be matched with this one, and so forth. So this is how we create data sets for training for specifically those examples. If you just have one value, you still have to create like an array of one value. It has to be an array. It can't be just a number. Yeah, this already demonstrated. And this is batch training. So sometimes you have lots of data and you want it's important for performance reasons, and also it normally provides better training if you train on several examples at the same time. So like if you have, for example, 10,000 examples, and then you choose to train on 4 examples at the same time, that means that this neural network is replicated 4 times, and it's fed with 4 examples at the same time, and then the error, this correction step, it happens once per batch. So you could have a batch of size 1, then you go 1 example per example, but then this thing might not get you there quite as efficiently as using batch training. And usually there are some optimal values depending on the model, but I'd say like in this case it's just a demonstration for like this number 2 here, but generally somewhere between, let's say, 10 and like 100 it would be a good batch size. It's also like it's highly variable, but let's say, depending on your data, depending on the images, sometimes using large batch sizes reduces the training performance, or just takes too long to compute. But generally speaking, it's good, like if you have enough data, like let's say infinite data, usually your batch size is going to be within those ranges. In some exceptional cases, you'll have to train one by one, or you need to have smaller batch sizes, or you need to have batch sizes in thousands. There are some additional options we have here. This means don't print anything during training. Like if I change this to 1, then I'll see some training progress, which sometimes is desirable. But because we have, not so many examples and 12,000 epochs, it just prints lots of junk. So we don't really want that. Now I probably can't stop it. Yeah, this one I'm choosing restart kernel basically means kill Python and start it again fresh. So then we do have this reduce learning rate on plateau, means that every time it's found that the network doesn't train anymore, it drops the learning rate by this factor a little bit until it reaches this value. And patience means for how many epochs it needs to wait, that nothing changed at all. Then you have checkpoint. That's a good thing that saves your training state. Like if you have very long training models, then you always will have the best state saved in that file. Save frequency here, you might want to change this. Basically, I think that's number of examples after which it actually checks whether it should be saving something or not. Because if it checks it like every time after every step, then this would impact the training performance, and so it only checks it this often. Now this is self-explanatory. We already looked at this. It does work because prediction also comes like you can see that this outer square bracket actually means that we are not passing like one example, we're passing an array of one example. So when I'm getting the output from it, I'm also taking only the first element. This is the data structure that needs to be followed for Keras, even if you just specify one value. And this is a numpy because with this imports.py that I created, this run imports. The first cell, it imports numpy to the top level, and you can just use it without prefix. So this is actually np.float 32. So if you have some, those clearly look like integers, but this float 32 takes care to convert them into a floating point number format. And then when we are printing the result, obviously, like neural networks are not precise. Like if we print without rounding, then we'll see lots of rubbish and like something like the 5th, 6th, 10th digit, and so it's best that we round it. So example 1 only works for sequential numbers, and we already looked through it, like it was supposed to happen at this point here, but we already went through this. So now we can go to example 2. And example 2 is basically a replica of this in TensorFlow in Keras.
I think, George, we are out of time.
Mm-hmm. Right. If we're out of time, that's where we stop. Yeah.
So we can basically resume from the second example onwards next time. So what we would do is from tomorrow there will be another meetup event on the PyMalta page where we will reshare another Zoom link and another session similar to the one of tonight, and continue from there.
Michael, I think should we plan for it like in 2 or 3 weeks time? What do you think?
Yes. So tomorrow the event will be available. Yeah, does anybody have any questions on what we just saw with George?
Yeah, I just want to give a small preview on what we're going to have.
Please.
So I'm going to explain, like I'm just jumping through slides forward. So I'm going to explain overfitting and what exactly it is. So let's then this would be one example of how a network should work and overfit. And it's overfitting things. Then we're going to look at some, data approximations and also at ways of like underfitting, overfitting, considerations for machine learning size. Then at some point, I'm going to explain briefly what convolution means and how you, for example, find letters in a graphical text, like in this case, letter A. So this isn't going to be, and then at the end, there will be this vowel detection example. There are some audio files there with me being very silly, pronouncing all different types of vowels, and that also we're going to go through. Right, so that's
very cool.
it.
Thank you very much, George, for your time.
That was really good, George. Really good.
Mm-hmm.
Yeah.
Thank you.
So
yeah,
we'll have
please.
We'll have the recording and we'll share it. And apart from that, we'll have the feedback form, which Michael already shared. It would be amazing to get some feedback from people just to make this better over time. Yeah, and then we'll plan for the next one.
Yeah, if you need some technical support or you'd like to ask something, I'm on the Telegram channel, and you could just send me a private message or send it to the channel, and then we can kind of split off to a private session or somehow else, and I'll help to install any virtual machines or explain any bits of this. Like, we still didn't get to the guts of the advanced machine learning, but yeah, please don't hesitate to ask me anything.